going. However, all participants will not have the possibility to speak, but you can pose your questions in the right side where there's a chat. If you post that to everyone, then we will try to ask the questions for you to the presenters. Well, first of all, this is we have done similar webinars, but this one today is focusing on the aquaculture, and I will be doing an introduction to the VIDA and to the demonstration vouchers. Afterwards, we have Jesper Heldbo from AquaCircle that will present the aquaculture challenges, and following that, we will have different pitch style presentations, and there will be 5 different ones. We have one from Jürgen Korb, we have one from Rado, Antonio, Carlos, and Benjamin. And again, please use the chat if you have any questions. So VIDA is the abbreviation for value-added innovation in the food chain. And what does that mean? It actually means that we're focusing on the intersection between the food, energy, and water, and the key enabling technology sectors. This is a EU project from InnoSoup that was approved in 2017. The project started out here in April last year, and it's running until March 2021. It's focusing a lot on supporting the SMEs by cascade funding, and as you can read, there's of the total budget of 4.5 million euros, 3.5 million euros are actually allocated directly to the SME innovations. Yes, we have 10 partners from 7 countries, and from which we have 8 different clusters involved. So, the scope of VIDA is that we want to nurture and we also want to harvest the growth and innovation potential within the SMEs, but working across the different European food chains. And we want to do this because we want to drive the European global competitiveness and also the development between the different intersections. And as I was saying, we have different VIDA partners involved in this project. We have partners from Holland, the Center of Expertise Water Technologies. We have the Stickling Water Alliance. We have Aragon Food Cluster. We have ZINNAE. We have Baltic Net, Plasmatech, Food Processing Initiatives, Lombardy Energy Cleantech Cluster, Nano Progress, SPI from Portugal, and Clean from Denmark. So the VIDA challenges within the food sector. There's a lot of challenges, and some of the challenges that have been focused on has been where we've seen that this nexus is very relevant. And this goes from, you can see from the food, focusing first of all on the fish farming, also breweries, meat production, other areas. Please notice that this list is not exclusive. This is some of the areas that we have seen that is relevant. So the most important of it is, of course, the funding schemes. How can you get access to these funding? And we have 3 different funding streams. We have the innovation support vouchers, we have the validation vouchers, and we have the demonstration vouchers. So the innovation support vouchers, these are rather small ones. They are from 1,000 to 5,000 euros. This is going to be an open call in 2019, and there's the expectation that only one SME is participating and applying for these vouchers. Then we have the validation vouchers, 10,000 to 25,000 euros. Again, open call in 2019. Time period again 6 months, and we are only expecting one SME to participate. What is important, of course, is that we are talking about the right TRL levels. So we are focusing our efforts within the TRL level 5 to TRL level 7 to 8. Sorry. The demonstration vouchers that we're focusing on today, especially, these are the big vouchers, and they are from 20,000 euros up to 250,000 euros. We're going to have 2 calls in 2019, and there is a bit longer time from 6 to 12 months, and we are expecting more than one SME to participate. So when we're talking about the time frame in terms of the money, is that the money is actually spent during this period. So who can actually apply? What are the criteria? In order to get access to the funding, you need to have an SME status based on the European definition of SMEs. So that is meaning employees less than 250 and balance sheet less than 43 million and the annual turnover less than 50 million. Then the applicants, they need to be active in one of the specific sectors that I mentioned before, so that's food, water, energy, or key enable technologies. And you need to be sure that you are financially stable, and there you need to fill in an application, declaration, and you have to be having your headquarters or be part of one of the VIDA clusters. So as I mentioned in the beginning, we have covered more or less big parts of Europe. So we have Portugal, we have Spain, we have Holland, Germany, Italy, Czech Republic, and Denmark. And if you are in doubt of who you should speak with from your territory, it is possible to go to the vidaproject.eu website, where you can find your contacts of the partner and where they are specifically located. The demonstration vouchers, the one we're going to speak a bit about today. So again, we have the 2 calls as I mentioned this year. We have the first one that is opening now. You can already on vidaproject.eu find the information of the criteria and the voucher schemes for the applications you will be able to access within the next 10 days. So it's not open yet to do the actual application, but it will be ready in 10 days from now. And then you have until the 29th of March to submit the applications. We will also have a second call this year, starting from the 1st of August and running until the 31st of October 2019. Again, the TIL level, 6 to 8, and having more SMEs working together. You could say that what is important with these demonstration vouchers is that you can make a difference. And this, we believe, can be done by working together among the SMEs. As said, there's quite a lot of money available, up to 250,000 euros. However, one SME can a maximum gain 60,000. Sorry, 60,000 euros. That's the maximum. So, as you can see within the different activities you can use it for, there's the personal cost. There's also, you can use it for buying equipment, infrastructure. However, be aware that you cannot buy hardware or specific licenses for more than 50% of the total amount. So, but again, be aware, up to 250,000 euros, minimum 20,000, and 2 calls in 2019. Yes, the calls, they are published, and they will be published on the VIDA project.eu. As mentioned again, there's all the specifics already on the web page. And there will be specifics concerning the application schemes. They will be ready within 10 days. Yes, I think that's all from me from the beginning. As you can see also in the chat, there's the link to the partners and to the voucher schemes. And I will leave the presentation to Jesper Heldbo from AquaCircle. If you can unmute, Jesper, thank you.
Yes, thank you very much. There should shortly be a nice picture of me. Yes, coming up. It's me to the left. And I would start thanking you for giving me the opportunity to speak today. I represent AquaCircle, which is a business membership organization in Denmark, focusing on aquaculture and techniques for aquaculture, mainly land-based, and we are focusing on RAS, that is recirculated aquaculture systems, and that will also be the topic of my presentation today. So aquaculture plays and will play a major role in obtaining the United Nations World Goals. I will not come into which one of those. It's obvious that goal number 14 will be one of them, but at least 5 or 6 could be addressed by aquaculture. Here you see the amount of feed needed to produce a kilo of animal protein or meat. It says that fish is only 1.1 kilo to produce 1 kilo of fish. For smaller fish like trouts, it's even less. It's 0.8 or 0.9. For bigger fish, it's close to 1.1. And why is this? That's because fish are poikilothermic animals. They do not spend energy in keeping a high body temperature like you and me, or the pigs, or the fowls. They are also weightless in the water, so they do not spend energy to counteract gravity. Therefore, the energy saved is used for growth. And aquaculture, or in this case farming fish, is actually the most efficient way to produce animal protein. This picture is showing a historic and picturesque picture of what has been. It's a flow-through urban pond fish farm in Denmark some years ago. As you can see below the picture of the sheep, we have a picture of the fish, and fish in culture that needs to be fed. And today most farms use industrial produced fish feed that is pelletized or extruded. And if we go back 30 years, or maybe only 20 years, a lot of fish was fed with fish waste from fish processing plants or industrial fish species, which gave a lot of pollution in the receiving water bodies. What has not changed is that the fish has to excrete, so what goes in must come out. Ammonia from the gills, phases containing organic material, phosphorus and nitrogen, in the beginning as particles, but the substances will soon leak out and part of them will be dissolved. If nothing is done to collect these substances in the farm, they will be flushed into the receiving water body and create the pollution. During the last 15 years, the Danish aquaculture sector has changed dramatically from outdoor flow-through urban ponds, as mentioned before, to advanced indoors recirculated aquaculture system. It's also changed from low biomass in extensive systems to high biomass in intensive systems. It's also a change from pure craftsmanship to digital assisted management. It's also a shift from export of fish to export of advanced equipment. We just have an analysis of the export value of aquaculture technology from Denmark. It's 2.8 billion Danish kroner. You have to divide by 7. That is almost 4 million euros. So it's quite a big export. So this is a graph or illustration of what we have to the degree of recirculation with increasing use of technology. The traditional farms, that is the flow-through urban ponds. It is, can I point with this maybe? No, maybe not. You can see the O on the slide with on the x-axis. It's the flow-through normally used water from rivers and creeks in an amount of 40 to 50,000 liters per kilo of fish produced. There was no or little equipment for enhancing the production or reducing water consumption, but although a sedimentation basin before the outlet from the farm has been mandatory since '89. Also, a limit of feed to be used on the individual farms or feed quota was imposed as a measure to reduce the environmental load from fish farming. Few farms took advantage of aeration, like paddle wheels, and simple reusing water once more. But if you go up the line, you can see we start with aeration. We may change to oxygenation and degassing to remove CO2 or nitrogen gases, and of course add dissolved oxygen to the water. Then we go further up, we add mechanical filtration to remove organic particles. We can introduce biological filtration to remove ammonia, and also here some organic materials, mainly dissolved substances. We go further up, we introduce disinfection by ultraviolet beams and or ozone And in the more very advanced system, we also take care of the nitrate. The ammonia is converted in biological filters to nitrate, and then again from nitrate to nitrate. But even in some places, we want to remove the nitrate and make it into free gaseous nitrogen. That is called denitrification. It's without oxygen. And eventually we can remove the phosphorus and the brownish color, which very often is in the water in recirculated systems. So in Denmark, the game changed from traditional flow-through system with earthen ponds towards ponds made of concrete. So, sorry. This is a raceway system for trout, and there's different technologies involved here in cleaning water. The result of this change was a great reduction in the pollution or the nutrient outlet. 50% of nitrogen could now be cleaned before the water reached the receiving water body, 65% of phosphorus, and 95% of organic material. So compared to the flow-through system, we had the possibility to have a bigger and more homogeneous production. We have a better feasibility, that is money, of course, up to 30% of profit. Before it was only 5 to 6% for the farmers. And we have less outlet of medicine and chemicals due to disease control and increased turnover time in the cleaning facilities. I'm sorry, but now we have to be a little, oh no, this is just to show you the amount of technology introduced and what can be achieved. Here we have the organic matter, the blue one, nitrogen is the yellow one, phosphorus is the red one, and phosphorus is the hardest to get rid of. We need to have a chemical removal of phosphorus in the very end. So a lot of people, they claim that they have 90, 95, 98% of recirculation, and that's rubbish because percent of what? So the proper definition of recirculation is the amount of water we need to add to the system per kilo of feed we put into the system. So in this example, we have a change of water. We add new water every day, 120 cubic meters, and at the same time we feed the fish with 300 kilos of feed, which give us a water exchange per kilo of feed to 400 liters. So the clever fish farmer, he may even use less than 1 kilo of feed per kilo of fish produced, or the not so clever may use a little more, but that's nothing to do with the system. This definition of recirculation is actually defining the capability of your water cleaning facilities in the system. So actually, recirculated aquaculture started 30 years ago when we first started to farm eels. So you may say that the general trend is that RAS wins out. RAS is, as I mentioned, recirculated aquaculture system. It is safe to say after 30 years of product maturation for this concept. Efficiency on the technical side are gradually corrected, but must be seen in the light of biological conditions in the biofilter, which have not been completely clarified due to lack of understanding of various biological processes in a biofilm, which is difficult to explain in all details. However, this does not mean that RAS is necessarily run at high risk of operational disasters if one understands the basic processes. So I tried to list a number of advantages for RAS. The basic idea is to farm fish in recirculated aquaculture system to reduce the amount of water needed. So we only have to add the water that we take away when we flush out the sludge, or what is taken away when we harvest the fish, or through evaporation. With a reduced water consumption, you may treat the water to a quality needed for the fish you farm. So very few liters or cubic meters of water, you can actually treat the intake water, and you can adjust the pH, the salinity, the temperature, and whatever to suit the fish you farm. And at the same time, you can treat the small amount of water effluent coming from the farm to fulfill environmental demands. In this figure, you can see the traditional pond farming. A lot of water was used, and if we go down to what you saw, the Danish raceway farm, it uses about 5,000 liters of water per kilo of fish produced. If you go to moderate recirculation, you can go down to 500 liters, and you can even go further down if you introduced denitrification and removal of phosphorus. And just to compare the amount of water, here highlighted in the red color, producing 1 kilo of beef, milk, pork, chicken, and so on. So also when it comes to water use, aquaculture is very competitive to other food production. This is just an example of keeping the right temperature. This is for Atlantic salmon, which grows best and have the best welfare between 14 and 16 degrees of Celsius. And as you can see, this is actually the best temperature for all stages in the life cycle, from even for the small, for the larvae, for the par, from the smolt, and for the big grow-out of 5 kilos. Also, the required area or volume for the production is relatively small, because a very high density and a high growth rate is possible in the controlled environment. Denmark, we now have 2 facilities with full cycle of production for salmon, and we have one of them has a capacity of 2,000 tons and the other of 3,000 tons a year. It's Atlantic salmon of the size 4 to 6 kilo at harvest. The area used to produce this fish equals 4 to 5 square meter per ton production, and salmon production requires both fresh and salt water, as you may know. And other new advanced RAS facilities in Denmark are for pike perch, for trout, and for yellowtail kingfish, that is salt water. So RAS system can be used for a lot of different fish species. So talking about RAS, we have reduced the risk of diseases because the amount of water we take in is rather limited, so we can treat and make the best chance of not introducing any pathogens or other unwanted agents. We have the possibility to measure all the quality parameters. Today is mainly digital monitoring, and in this way we can secure a stable production for the fish, stable conditions for the fish. Most of the add-up water, or the new water we introduced, is, as I mentioned, to replace evaporated water, and not least to the water drained from the system with the sludge. But most of the sludge is now collected by mechanical filters, and some when biofilters are cleaned. Common for these cleaning facilities are that they use some water, and the water follows the sludge. So the volume for storage of sludge can be quite small if the sludge is concentrated. Very often bioflocculants and sieve belts are used to dewater and concentrate the sludge. But even decanter centrifuges are used somewhere, some places. So with very little water intake and consequently very little effluent and concentrated and odorless sludge, RAS can be established in, for example, industrial areas near big cities or at the market, so to speak. This gives also an opportunity to save transportation costs. Remember that fresh salmon flown from Norway to USA will add at least an extra $1.50 to the retail price, or to Japan or China will add $2 more. So you can say if you produce the fish at the market, you can save the transportation cost. So Danish turnkey suppliers has established land-based salmon farms in China, 3,500 kilometers from the sea, in Dubai, in Poland, and big facilities are now under construction in Norway and in Florida, just outside Miami. But, of course, we have some challenges and we have some drawbacks. The system is relatively advanced and is dependent upon a regular power supply. It requires an emergency power generator and a security and alarm system, which is in function at any time and under all possible conditions to secure continuous operation and good environmental conditions and welfare for the fish. So moving from traditional fish farming to RAS significantly changed the daily routines and the skill necessary for managing the farm. We now have two animals in the system, the fish and the bacteria in the biofilters, and the fish farmer has now become a manager of both fish, water, and bacteria. And the task of managing the water and maintaining its quality has become just as important, if not more so, than the job of looking after the fish. The traditional pattern of doing a good day's job at the fish farm and then going home has changed into, we have turned on a machine that runs company 24/7, 360 days a year. And also, if disease is introduced, the environment also is in favor of the pathogens, and one has to act swiftly. Therefore, a facility is normally constructed with several water treatment loops, not just one, to contain any diseases to one compartment and fight it there. It is also rather costly to invest in RAS system. The increasingly degree of techniques introduced is merit in the needed investment. Therefore, RAS system, until recently, mainly has been introduced to the fragile first life stages and to expensive species like salmon or marine fry or fingerlings. No RAS below 1,000 tons for the full cycle production or grow out is feasible. The Danish converted truck farms should produce about 600 tons to be feasible. Of course, this will be different for production of early stages of life, like smolt and from marine fry or fingerlings. In the table here, you see new and old. Here, it's if you construct a new plant or if you convert an old plant. So you can see here in the column number 2 from the left, the amount of water needed. In the column number 3 from the left, you can see the amount of energy used to run the plant. And in column number 4 from the left, you can see all the techniques introduced to control the water environment. And in the last column, far to the right, you can see the total investment for 1 kilo of production capacity. So you can see the intensive recirculation system is more than 10 euros per kilo of yearly production. We also have problem with off flavor. Taste is off flavor and off taste is connected to the number of organic particles in the water and the management of the biofilters. The DNA analysis of bacteria strains in the biofilters shows that more than 10,000 different families of bacteria is in the biofilters, and I think about 25 to 40% of them are able, under unknown conditions, to produce geosmin, and which create this off flavor and off taste. So removing as much particles in the water will reduce the problem, but may not get rid of the problem. Footprint of RAS facilities are big. Energy demand is high. Already mentioned, the investment is high. Off flavor, off taste, and also in some cases we have early maturation. We have a cascade effect. For instance, amongst salmon males, they start to get sexually mature already when they reach maybe 1.5 kilo, and then they
Jesper,
stop eating and stop growing, and that's
we cannot hear you. Suddenly the sound stopped. Now.
So this is some kind of, sorry. Actually, some part of the sun. In future, there should be more paid more attention to the hydraulic design. We have had some unexpected and accidents with a lot of fish being killed due to the sulfur hydrogen generated in patches where we have bacteria that produces this. Also, we have a strong and acute need for skilled personnel to run the systems. Just to finish up quickly, some trends. Growing bigger smolts in Norway, Scotland, the Faroe Islands, Chile, Tasmania, they are producing or setting up facilities to grow smolts. Instead of 200 grams, they can grow them to 1 kilo now to create a more robust fish for the life in the sea cages, in which they will spend less time. As already mentioned, controlled full life cycle in land-based system. This is a picture of what is going to be ready this spring in the southern part of Norway. We will have new species in wrasse. Already mentioned pike perch, Seriola, that is the kingfish, grouper, barramundi, bluefin tuna. It's all there already around the world. So it's not just in Europe. So it's possible also for Europe to produce more fish through aquaculture, even though there is a lot of competing of the land needed and other interests. I think that wrasse is a very good answer to the question of how we produce more fish in Europe. This is just to show you a pike perch facility. This is for the Seriola, the yellow-tailed kingfish. Big facility.
Thank you very much, Jesper, for a very interesting presentation. There's been a lot of questions, and some of them have already been asked during your presentation or answered from other participants also. I will suggest that afterwards we also share the email if somebody is interested to get in more in-depth dialogue. There's one thing I'm sure you can give a short explanation about, is that we're talking about wrasse on land. Could you just give a brief explanation of the difference between the systems on seawater and the land-based?
Yes, I'll try my best. Even the marine farms are depending on fish starting their life on land. Actually, all fish and crustaceans in aquaculture have to start their life in land-based facility. When you move the salmon or the trout, or if you have marine species to marine farms, you have very little ability to collect the effluent. So you will actually, all the nutrient will pass untreated into the marine environment. You can have INTA, that is integrated culture, where you may have mussel farms and you may have seaweed to pick up some of the nutrient, but until now they have not shown to be very effective in Denmark or in Europe. So when you have marine farms, you have to take into consideration the water current to take away or dilute your effluents, and in coastal areas this is very difficult. And in Denmark we have just had a plan to expand the marine farms, but it should be far away from the coast, so in offshore position. In Norway they are looking very much into to build what is called contained marine farms, where they take care of. Actually, they're not very interested in taking care of the nutrient effluent. They are more interested in developing systems that will lower the pressure of salmon lice to keep the lice outside the marine farms.
Okay, well, thank you very much, Jesper. I'm really sorry we will not be able to ask all the questions. You might have a look into the chat, and then afterwards we find a way of answering some of the specific questions. I would like to introduce the next speaker that might also have some of the answers to the last question of what is the next big innovation needed. I'm happy to present Jürgen Koch from Leibniz Institute for Plastic Technology. Welcome, Jürgen.
Thank you, Martin. Thank you for the opportunity to present our work and our approaches here in the webinar. I don't know if I have all the answers, but I definitely try to give some answers, or at least present some ideas that could eventually develop into an answer. We are not really dealing with aquaculture on a first principle basis. We are dealing with water treatment, and more originally we are dealing with plasmas and the generation of plasmas, and in particular with respect to water treatment. And with these non-thermal plasmas, we are able to provide, on the one hand, more efficient methods for oxidation than, for example, ozone, or more selective and more efficient methods for the elimination of microorganisms, for example, by pulsed electric fields, in comparison, for example, to UV treatment. So, as a research institute, we are trying to constantly and preferably work together with industry to develop solution-driven approaches for current problems. I have only a short pitch, and I would like to present you the general overview, and I'm happy to entertain any questions either in this webinar or by email afterwards. So, what do we do when we talk about plasma treatment? And what's the use of it? So I hope while I'm scrolling you actually see the next slide. And what's the use for agriculture? What we are doing, whatever method we are applying, we are using electricity. And on the one hand, with the pulsed electric fields, we eliminate microorganisms, and that, since it's a physical mechanism, including antibiotic-resistant bacteria. This is in fact a very old technique that is used for drinking water purification already since the 60s, because the process that it's working on is disrupting the cell membranes and tearing microorganism bacteria apart. What we do not get with the pulsed electric fields is an effect actually on organic compounds. So, and this is what we provide with non-thermal plasmas, and they provide a very transient chemistry to decompose organic compounds. The most important radical here is hydroxyl, which has a higher oxidation potential than ozone and is rather short-lived. So it's also not sticking around forever or for a long time in the water, but is decomposing again to water within very short time. The main application for that is actually the treatment of persistent pharmaceuticals. But what has also been composed, and I have not included that, is odors like geosmin, which we've done in previous projects on aquaculture. So the unique advantages of these technologies are you do not need further chemicals. You do not need chlorine. You do not need hydrogen peroxide storage. You do not need an ozone generator. But what you do need, you need electricity, as was already pointed out before, that this is changing actually the game and the way that things are being done. However, with the electricity, now it's actually an on-demand system. You can switch it on when you need it, when you actually do have a problem, and you can crank up the power if you actually have high levels of contamination and want to reduce them, or you can tune it down if you have only a low level of decontamination, or if you don't have any problems, for example, with certain bacteria, you switch it off completely. The main advantage is that in recirculating systems, you can reduce the freshwater intake because you can make your water cleaner. What is also an emerging problem that we are facing here, in particular in Germany, is actually effluent. I heard just in the chat that that is probably not a problem, then you don't need it, but in particular pharmaceuticals and antibiotics especially are under scrutiny in Germany. And what's in the first bullet point, I always said that you can eliminate a lot of the harmful microsubstances. What you cannot do, also to say that, we are not able to remove nitrate and nitrites, and we are not able to reduce heavy metals. So we can do a lot of things, but there are some things that we cannot do with plasma. So some examples, how does it look like? There are many different ways to generate the plasma. All of them have in common that you need high voltages in one way or the other. They could be AC high voltages, or they could be pulse DC voltages. And then you design an electrode geometry that is suitable for whatever excitation scheme you actually have. And that could be that you have pulse DBD or coronal discharges, the first picture with short high voltage pulses, where you spray the water into the discharge. And just one of the examples what works very well, which doesn't work very well with ozone, is, for example, the reduction of hormones, and in this case, one example, phenyl estradiol. Another example is you treat just the water itself outside, that doesn't have to be in the main tank, and then provide it for a short time that's lasting at most 1 or 2 days and can be diluted with antimicrobial properties. The laboratory experiments that are shown here is an example for S. aureus, where you have indeed a 6-7 log step reduction, which does depend on the salinity of the medium of the water that you are treating. And the last example, that completely the opposite, you're generating the plasma inside the water. And yes, you can get reduction of pharmaceutical compounds, and at the same time you can also get a reduction of microorganisms. On a side note, this discharge in particular is also increasing actually the oxygen in the water, the oxygen concentration in the water as a side effect. But these are just 3 examples out of many others that can actually be done, and they have to be adopted with respect to the problem that you have and what you want to do. All of the plasmas in general have in common that they provide different physiochemical mechanisms to destroy organic compounds or microorganisms that can be tuned with respect to the plasma in one way or the other. So most importantly, with the plasma, you create radicals, active species, that leads to advanced oxidation of cell coats and membranes, also of biomolecules, and you provide substances like peroxynitrates that are known to interfere with metabolic processes of microorganisms. Electric fields, as already mentioned, is a very old method to disrupt cell membranes. In some of the plasmas, you can generate strong shock waves that lead to the mechanical disruption, and you can see from these 2 examples there is actually no protection of the microorganisms that we know so far, and no resistance. UV is another method that can be done. In comparison to other methods, however, UV is very successful in drinking water because it's clear water. If you have turbid water, pulsed electric fields and shockwaves and plasma in general are more efficient because they don't care if the water is turbid or not. Then you have some other effects that come along with the plasma, that in a short volume you have transient temperature gradients and you might have charged particles. So this already brings me to the end of my presentation. And so I would be happy to hear your ideas and your problems, and if we can actually work together with you, if we have a solution for you. We do this a lot, and following our motto, which is from idea to prototype. We are a research institute. We are not a non-profit organization. And depending on the specific problem, we develop a plasma source and an application, or we at least have a look if we can actually solve a problem we might have. And that can be at a very early stage. that we just do a proof of principle studies, or we just do the investigations on some basic mechanisms. And ideally, when it does actually work and when we are convinced that this has a potential, we would like to engage in research and development up to actually the setup of systems for the treatment of a complete aquaculture. However, we would probably not do this alone, but would try to work together with the companies who are actually manufacturing on the site. With that, I would like to finish, and I see a lot of questions which I was not able to follow, and I'll leave it to Morten if we are trying to answer them here or later.
Well, thank you very much, Jürgen, for this very interesting presentation. As always, we do not have a lot of time, but I think the questions are very, very relevant, so maybe not too long an answer. As you're saying, you are in a research institute, but you would like to develop this further. Okay. Do you have any specific ideas concerning the TIL level and also in terms of cost?
The technology readiness level. If I have to look at the table, it's not at the aqua farm. It's at the laboratory stage, but it's demonstrated. Don't ask me what the number. I think 4 or 5. So it's not at the product stage, or 4 or 5 laboratory demonstrated application. That's what we have. The other question about the cost, that now to say depends on how far you have to go when you actually want to reduce something. As a comparison, wastewater treatment plants operate with an energy cost of 1 kilowatt-hour per cubic meter. This is about the goal and what has been demonstrated also for some of the pharmaceutical substances. If you have very persistent chemicals, organic compounds, you must go higher in the energy cost. That's with the tuning. But as a ballpark number, remember we are working on something of the order of 1 kilowatt-hour per cubic meter. Has the technology been tried in seawater? No, it has not been tried on seawater. The conductivity of seawater we've been staying away so far. It's most appropriate for freshwater farming, because seawater with the electricity, some of the technologies, the losses are too high. But however, the picture in the middle, when you treat actually the water on top of it, that works actually better on seawater. But here we are not as far as with the other technologies in treating water. Is there something else? Does this decrease the viability of the geosmin producing microorganisms? Yes, it does, but we have in this case only looked particular actually at in the geosmin itself, which our challenge was actually the analysis. We got it down to under the detection limit, because for us that was not such a nice substance to work with. But yes, the bacteria are reduced without being specific, and the substance itself. Now they are coming more. There were some tests with geosmin. That's what we've done. How is it different from electrocoagulation? Electrocoagulation, you usually work with very low voltages, but high currents, and you have to add a flocculant, which has to be removed. So this is not a filtration technique. All the techniques that I showed you is not a filtration. It's actually destroying substances, decomposing them, or inactivating the microorganism. Okay, if there are no further questions,
okay.
Thank you.
Well, thank you very much. Thank you very much, Jürgen, for a very interesting presentation, and also a lot of questions, which is very, very nice. The next presenter is Radu Mitya from Semilla IPSA, and we are looking forward to hear more about your system. Thank you very much, Radu.
Thank you, Martin. I hope everybody can hear me clearly, and thank you for this opportunity to present our latest developments from our lab. So working with the semi-circular system, this product is actually a spin-off from a research project where we studied aquaponics in autonomous system, like automation based on the data. So what we did a large sensors network for gathering big data sets from these aquaponic systems, or growing fish and using the waste of the fish to grow plants. And we managed to take all this kind of data about the water quality, the environment, and other lab analyses together and do kind of models that we verify through experimentation. And once validated, we use this new information as input in the automation. So we are trying to pave the way to more autonomous data-driven aquaponic systems. Why is this interesting in this context of speaking about aquaculture? Is that looking at our data, which is based on the lab scale research, we have seen that if you look at the red line on the bottom, on the left we have cultivated carp, which didn't really adapt it to our system, so had a relatively low growth, but a good nitrate production, so the nitrification process was very good, and that's what we aimed for our plant. And later growing African catfish, this type of fish adapted really well to our system, so had a really good growth, but then the dynamics of the nitrification were really different. And what we have learned from this process, we are still investigating the reason why these dynamics were so different on type of the fish and the load method we have in the system. But what was really interesting to notice is that although we had a lot of data about the system in general, the water quality, we did lab analysis and so on, we didn't really know exactly what happened with the food that we gave to the fish. So giving them an input based on the literature and so on, it's not necessary that all the time, even the parameters are optimal, all the time the fish will eat all the food. So the leftovers are dissolved in the water, leading to changes in the water chemistry that further influences the fish appetite. So they will probably eat even less, and this leads to sort of a problems in the system, especially when it's recirculating. So what we thought we need to develop a solution to both gather the data and optimize it in real time. First one is manually, so you need a person to feed manually the fish, see how much they ate and remove the excess feed and optimize on the go, but this is very high labor intensive. So the second one would be a more supervised one, using the cameras from the tanks, looking when the fish didn't eat the food, and if it's in thresholds of dangerous thresholds, then somebody should go to the lab and optimize it, but this is also not very feasible because you would have to log in 4 to 6 times a day and always observe what happens with the feed input. So the third one would be naturally a more artificial intelligence based system that would feed, gather the data and optimize in real time. So we set on developing the third option, and this is a very simplified architecture of how things are working. So we are feeding automatically the fish. The leftover is recorded automatically by cameras as images that are fed to a machine learning algorithm, which will learn to transform the image part in a quantifiable data, and based on also the data from the water quality, what comes from the system, a decision can be made in optimizing the next feeding cycle. In this scenario then, feeding the fish, having a leftover, this leftover will be recorded by the camera. The system also understands what the leftover will do to the water chemistry, and based on the experimentation that followed, will optimize the next feeding, for example, feeding less the fish, and this will result in zero waste of feed. And this is a more sustainable and long-term way of growing the fish without having all sorts of problems relating to water toxicity. So we had a lot of challenges in developing not the machine learning algorithm, but getting accurate data to make this kind of learning process reliable. But in the last couple of weeks, we resolved most of the hardware problems, and we developed the models. And the first model had an accuracy of 90%, and you can also see in the images below with the interface that we've built that the system could understand if the fish ate all the food, if the fish ate less or more than 50% of the food. And based on the new data that we are gathering, this precision is always fine-tuned. So why is this important? It's not just because of our obsession with getting more data and understanding this complex ecosystem and the process that's happening from the waste of the fish to growing the plants, but we have seen that solving small issue as the feed input and precision of feeding the fish will actually lead to solving a lot of environmental problems. Aquaculture being one of the fastest growing technology, the feed is one of the most expensive parts of the aquaculture, and uneaten food leads to water toxicity and pollutions. Farmers have to use antibiotics, and this kind of solution could really touch on a lot of UN Sustainable Development Goals. So that's why we are passionate to take this to the next step, and with the current resources we have now, we could probably bring this product to a TRL 4, let's say, and then we need more funding to make a proof of concept at the bench scale pilot, and later to develop demo cases with partners on actual aquaculture sites, and finally normally get this product to being commercially available. Thank you, and looking forward to connect with you and see how we can develop this kind of technologies further for aquaculture.
Thank you very much, Radu, for a very interesting presentation concerning this VIDA. There's been a different questions, especially concerning the first of all the pellets. So there's one question saying, how would this system work with sinking pellets?
Mm-hmm. So
is it something you try?
Yeah, so we developed this system right now with floating pellets, not with sinking ones, so we can use the camera on top to monitor the leftover. There are also technologies developed on academic level with sinking pellets using more color recognition and image processing. But that's a bit more complicated, and we have seen that working on this part and getting it to a very precise way of using real-time optimization of the feed would be very useful, and from there we can go on more in depth in developing new technologies, because we need more diversification and scaling up the system.
Mm-hmm. Okay. Another question is concerning the how to make sure that the fish get the right distribution, like how to solve the distribution of the fish. In net case, in the sea, small fish is often suppressed to the lower part. How to secure that they get fed? Is this something you have been focusing on?
Yeah, this brings more complexity to the whole system, but that's why we need to collaborate with companies that bring the knowledge and expertise of aquaculture, and try to respond to those questions building on what we have developed until now. So that's our goal, to connect with more experts in the field and respond to their needs. Because right now we just, as I said, spin off from our research project concerning aquaponics. It's an important input that we didn't have as data to understand the whole process. And we have seen through our last experiment that we could actually even control the nitrification process, we can control the feed. So this responds to our needs right now, but we have seen the impact that can have on a large scale. So that's why we want to take it to the next level and work with experts in the aquaculture and develop this system further, because it's very powerful using these machine learning algorithms.
Okay, well, thank you very much, Radu, and thank you very much for this open invitation for further collaboration. And I encourage everybody to reach out to Radu for further collaboration.
Thank you.
Again, I'm a bit sorry that we're running out of overtime, but as the presentation is so interesting, We will of course continue. The next presenter is Antonio Ida from Algaria. So
yes, good.
Welcome, Antonio.
Good morning, everyone. As I said before, I'm Antonio from Algaria. We are a company that's producing microalgae, and we would like to exploit the power of algae. Now, I'm presenting here our new product, a biopond, that is able to creating value from residual effluents. So, to address the sides of the problem, sorry, I have some problem in the slide. Manage. So, the sides of the problem is we had a case of Italian environment, so we produced 3 millions of cubic meter of these effluents. That is that have a consumption of 3 or 4 terawatt hour. This means 1 or 2% of the total energy demands in Italy. This agro-industrial effluent is characterized by high COD, so COD load, and is a plenty of nutrient. And right now, the state-of-the-art of technology use aerated big pond that oxidate partially the organic matter, having as output a residual activated sludge. The drawback of this technology is the partial oxidation of the effluent and the loss of the nutrient in the sludge. So an advanced technology has been proposed using algae in the pond as a source for oxygen and for nutrient removal to sustain the algae growth. But this technology is affected by the unstable balance within the 2 organisms that work together in the same environment. And usually bacteria take over the process because bacteria are grow fast and are more adaptive to the environment. So to overcome this problem, we developed a biopond that is based in a bioelectrochemical fuel cell technology. So basically, we divide in 2 chambers the effluent flow with a conductive materials that allow the diffusion of anions and nutrients. From bacteria, the anodic chamber, to the algae chamber, so the cathodic chamber. These allow the translocation of different nutrients and anions that generated electrical force that is applied to the system itself and improve the translocation of the nutrients. So this will overcome the problem that we saw before of the balance, the biological balance. And now we are running the demonstration facilities that apply this technology, producing biomass, algae biomass. The idea is to valorizing the biomass in a future product like aquaculture feed, because algae are plenty of protein or organic minerals for fertilizers or extracting color dye. So the advantage of the process is the improving the efficiency of the system for wastewater treatment, the easy integration for the existing technology, I mean the aeration pond, in reducing the overall energy consumption with high nutrients removal and reuse, and valorize the market bioproduct. Right now, we are in a demonstration scale, and we would like to explore the market opportunity for the bioproducts. Thanks for listening. Are you there?
Yes.
Yeah. Okay. I'm finished.
Well,
I'm quite finished. five slides.
thank you. Thank you very much, Antonio. I'm a bit curious concerning the demonstration you're currently running. You're talking about also the reduction of the energy consumption. Would that be able to elaborate a bit on how you see this reduction in which scale?
Sorry, I missed some word. What do you mean? We have a demonstration plant now running in our company facilities. We trial with different effluents, and now we are using liquid separate from biogas plants. That it's running well right now. Well, basically, the technology is running well with 90% of consumption of COD in the effluent, and uptake of the quite total uptake of the micronutrients in the algae culture.
Okay. There's one question concerning the specific alga you use.
Sorry, what about the data?
There's a question, Antonio. What are the alga specifics?
Actually, the algae that we use right now is spirulina, but it depends of the effluent that we are going to use. Right now, the system is optimized for spirulina bioproducts.
Okay. And another question, how do you control and combine uptake, efficiency, and extraction of the microalgae?
Yeah, actually, I control the system, the uptake efficiency, taking data from algae culture. I mean, we had the system totally wired with sensor, and we can control online all data. So also the uptake of the nutrient.
Okay. There's just a following up question. Let me just see if I can see it. It disappeared from my screen, unfortunately.
Are there other questions?
Yes, one extra question is, and how are the contents of the microalgae compared to from the ocean?
Sorry, I didn't take the ocean means.
Not clear the question. Okay, but Antonio, thank you very much for an interesting presentation concerning your system, and also the opening up for further collaboration. Thank you very much.
Thank you too.
The next presenter is Carlos Espinal.
Yeah, everybody. Can you guys hear me?
Yes, we can.
Okay, good. So I'm gonna use the opportunity to pitch two products that we're developing. So bear with me if I jump from one product and the other. Please take your questions. Go. A quick introduction to this presentation. Our goal is to go towards zero discharge in fisheries and aquaculture processes. So not only fish farming, but also in fisheries. And I will explain a little bit further some of the ideas that we have around that. Landing Aquaculture is a small engineering firm now doing a bit of research and development. We're based in the Netherlands. We started doing RAS, moved into aquaponics, bioflux systems, and we have lately come across people, clients, and partners with some wacky ideas or requirements, and we have put our sort of creative power into trying to bring solutions to them. That has led to us focusing more on R&D since last year. We're working on one EU project, short-term scientific missions where you go to a research center and do some work there, and a lot of small subsidies and grants for these sort of projects that of all these, we have one patent application going. It's the first time for us as professionals and a small company to go through that. It's a very exciting time. We have two products that we are developing and pitching this time. One is for vessels, and that can be adapted to land-based facilities, and the other one is only for land-based facilities. First one is called Deathline. It's a machine to treat blood water in fish processing and fish harvesting vessels. Basically, we are combining a dissolved air flotation technique with oxidation to remove color, organic matter, fish parts, and that can work in a vessel that is moving at sea, subject to the waves in rough weather. We can mount it on vessels and move it around. The other option that we have, it's a denitrification reactor that works with the sludge that is produced inside the raft. So that allows us to digest the sludge and in the same reactor. It's not too different from what is done at the moment, but we are trying to simplify that process for commercial application. You can see pictures of both technologies. Our blood water treatment technology is on the, I would suggest TRL7. We have developed a commercial prototype. It's deployed on a vessel at the moment. We're doing tests with blood water. You can see one picture of the samples that we're taking. So we are able to treat the blood water. But you can still see it's not completely transparent. It's sort of a drinking water quality, and we want to get there. The denitrification reactor, the prototype, is under installation. I have it just next to me, and we just need to go to validate the treatment efficiencies and the operational parameters of it. For the blood water unit, let me go back for a second. We need to basically record and document all the water quality, pathogen inactivation, the information that we need to get the approval from, in this case, Norwegian authorities as a disinfection device in aquaculture facilities. We are looking for demonstration partners for both technologies. For the blood water treatment machine, we are looking for demonstration in fishing vessels, harvest breeder vessels, and well boats. That includes North Sea and the Mediterranean. We're also looking to use this as a fine solids treatment device in recirculating aquaculture farms or in fish processing plants. In rat farms, we want to use this as a protein skimmer on steroids, basically. A very, very strong protein skimmer, able to remove watercolor and dissolve solids. After the demonstration, we want to get to TRL 8. We are about to design version 2, which is going to be a commercial version ready to sell, although even the prototype is already sold to a client, so that's a good sign. And for our sludge reactor, we want to jump quickly from TRL 7, where are we at now, to TRL 9. That's because the knowledge about denitrification is very well established. We just need a quick test with this reactor, making sure that all the concepts in the reactor work, and then we can go and sell it to market straight. I'm hopefully about to sell one of those in New Zealand in the next few weeks. For that, we need just demonstration partners, mostly in fish hatcheries and recirculating aquaculture farms, to work either on the rat loop, or meaning on the recirculation loop, treating the water, or using the device as an end-of-pipe treatment, so treating all the water that comes out from the farm into the environment. Denmark has plenty of experience with this application. That's pretty much it. I wanted to be brief. Basically, the technologies are developed, being applied. We just need one extra jump to bring them to commercial reality. And well, I'm very happy to talk to you guys for any opportunities that you think you might have to work together.
Thank you, Carlos. Very interesting presentation again. Few questions coming up. There's one concerning freshwater skimmer without any fluxulant.
Yeah. So the idea, if you go to the solver notation, generally yes, using flocculants and coagulants is sort of a requirement to have high efficiency. That said, for this blood water treatment machine, we wanted to keep it as simple as possible, and we wanted to make a first try without flocculation and coagulation aids. We have some other ways to compensate for the lack of this. So far, the results seem to be okay. So going to the freshwater skimming without flocculants, I would first try it without flocculants. Seeing that the microbubble generator unit that we have is quite good, and then you would see if we still need to bump up the performance of the system, then definitely I would add flocculants, as Jesper is suggesting. From Roberts, the final products of the blood water machine. On one hand, you have a foam condensate, which is very, very nasty. It's a pink foam, very stable, that you can pump into a waste tank and then dispose it on land once the vessel reaches the port. And on the other side, you just have a clean water that you can reuse again into the fish bleeding and harvesting process inside the boat. Those waters are used for chilling the fish. So when the fish is harvested, that water is chilled and is used to keep the fish fresh until the fish gets to the processing plant on land. Yes, thank you for that question, Radu. The main difference is simplicity. It's an extremely simple system. It's simply an upflow column where the sludge is settled. The column is filled with internals that keep or try to keep the sludge in a single place. And then the mixing of the sludge is done once an hour for a few minutes using an airlift. So the airlift is designed so the oxygen transfer inside the reactor is minimal, so you keep the anaerobic conditions, but the flow through the reactor is very big, so you can mix the whole reactor very quickly in a couple of minutes with just a pulse of air. That makes it very simple compared to mechanical mixing systems that you generally find in denitrification reactors. So that's the main design feature.
Excellent. Thank you, Carlos. Just an extra question concerning the deadline that you are having the patent pending at the moment, and you're opening up for collaboration, which is very admirable. What is the timing for the patent, and is there any concerns concerning that it's still open, or you're just willing to work with everybody?
At the moment, we submitted the patent application. The European Patent Office is reviewing it. So it's going to take another, I would say 4 to 6 months until we get some feedback on that. I mean, that means by our advisors, which I'm not a patent lawyer, but they tell us that from the moment we submit the patent until the final resolution, we are protected on our IP. So that is what has allowed us to sort of come out to the public and explain the technology freely. To be honest, without any worries. I'm not really jealous about it or anything like that. To me, I'm just an engineer, and I just like the technique and the science. So that's the status, yeah.
Excellent. So, well, thank you very much, Carlos, and an open invitation for collaboration. Thank you. And the next presenter is Benjamin Franchetti from AquaCircle Modena. You still here, Benjamin?
Yeah, hello, can you hear me?
Yes, we can. Very well. Thank you.
Okay. So, thanks a lot for inviting me to speak here. We don't work directly with aquaculture. We develop vertical farming technologies, but I believe that it can be coupled to aquaculture. So, yeah, I'm going to present you our company, which is Agricola Moderna. We're based in Milan, and we've been working on our technology for over a year now. Very briefly, well, I think this we probably all know. Just as a recap, essentially, agriculture today is unsustainable, and many reasons, among which, 70% of global water is consumed in agriculture, and a third of global energy is consumed in agriculture. Food that travels on average 1,500 kilometers goes through 28 different pairs of hands, and about 30% of crops is wasted. And also, the crop that does survive the long journeys, it's usually not as fresh. It lacks in vitamins. It's covered with pesticides and herbicides. And in addition, the population is growing. So we believe that we need the vertical farming as a solution, as an agricultural solution. So essentially, in our closed plant production system, Agricola Moderna can grow food more sustainably. Our technology is able to reduce water consumption by about 90%, while at the same time increasing yield by 10 times. The produce we are developing is what we say is superior to organic. In essence, it has no heavy metals, no outside ingredients other than the ones that the plant needs to grow. And we can grow the plant year-round. So it's not seasonable. It's on demand 365 days a year. And as discussed, it's pesticide-free. So we only grow natural plants with no pesticides, no heavy metals. And the plant is far, far fresher. So what is the solution we propose? So Agricola Moderna works on various aspects of vertical farming. We build the vertical farm hardware. So right now, as I'll explain, we're in the process of building a large 1,000 meter squared commercial farm. These farms are indoor, so they use LED light for growing the plants, and the water is recirculated, and the plants grow hydroponically, so outside the soil. One of the key elements of our technology is also our ability to collect the data, and at the same time we work with research institutes to even monitor the plant growth, both via visual recognition tools and using data analytics. And in parallel, we're developing our own farm management software that allows us to control the vertical farm. So where are we now? As of today, we've developed a pilot, what we call our R&D farm. This is a 50 square meter farm, which is in the heart of Milan, inside the Milan Food District. In fact, we are adjacent to cooking school, and we actually use the cooking school to test the quality of our crops in a qualitative way. In parallel, we test the actual nutritional values of our produce in collaboration with the University of Milan Agronomy School. As of today, we've tested the growth of more than 50 different plants, and amongst which we've been growing microgreens, but also aromatics, larger leafy greens, baby greens, mainly green plants, and we're also now testing strawberries. We've really concentrated a lot on the agronomy side of the business. So essentially, we've tried all sorts of density. We've tested various different light intensities, input conditions to the plants, nutrition, different growing methods. So we've really optimized our growing technique, and now we feel confident to move to a large commercial farm, which is going to be, someone is moving for me. I don't know. Sorry. Yeah. So yeah, so now we're confident to move to a larger commercial farm. We've already found a location just outside Milan. This will be a 1,000 square meters facility where we're going to be growing greens commercially for the supermarkets and for the distribution of greens. So here is just some images of our trials with the chefs. You can see here these are all greens that were grown inside the R&D farm, and we've been testing different different kind of combinations of plants. The reason we're going via chefs is mainly for image-wise, because a lot of people, the first question they ask is how does the taste and the quality compare to actual plants grown in fields, and most people don't realize that the majority of the plants you eat are still eaten grown in greenhouses. And actually, as the chef also said, the quality of the produce is considerably superior because it's far fresher, and also the nutrition value we have confirmed that it's higher than traditional growing methods via testing with Milan University. Briefly, here are some of the innovation work we're performing. We're working with the University of Rome La Sapienza, with which we've been doing deep learning and visual recognition of the plants. Essentially, we have 3D cameras installed on our modules, which are able to recognize real-time the rate of growth of the plant, and so eventually we will be able to completely automate the system. In parallel, we are also working with the Milan Polytechnic, which is helping us with the data acquisition side, so instrumentation of our vertical farm, so that we are able to continuously monitor the growth of the plants, both visually and digitally, and eventually have enough data which is able to optimize the growth behavior of the plants. Very briefly, just to show you some of our products, these are microgreens, which come straight out of our vertical farm. And here you can see our agronomer Luke, which has been growing aromatics, which also we be able to optimize their growth. And finally, just briefly on our team. Our team is made out of the CEO, Pierluigi, who has commercial experience in the food and beverage industry, myself, which I'm a PhD in mechanical engineering, and I act as the technical director of the company. But the first two hires we had were Luke and Tiara, so we've been really concentrating on the agronomy side of the business, and also we are collaborating with Dr. Duccio Piovani and Niccolò Cacciotti for the AI and the data science of the business. Thank you for your attention. I realize I actually haven't put in my email, so I'm going to write it here on the chat. And I hope we can find opportunities with aquaculture, which is definitely an industry that we find very interesting. Thank you.
Excellent. Thank you very much, Benjamin. There's been a few questions. One question, have you done any economic feasibility studies, business planning around the concept?
Yes, so I mean, the whole sort of, so first of all, we've done plenty of business studies for different countries. We've actually done one for Qatar. We're now doing one for Morocco. So we're receiving a lot of interest from especially hot countries where traditional Dutch traditional greenhouse technology is struggling. But also for a very, very hard market like the Italian one, you can only imagine probably the Italian market might be the hardest market to enter for this kind of technology. It's still commercially viable today already. But our bet is that in the long term, that the technology is going to become increasingly less expensive. The development of the product will be increasingly more automated, and our plan of using renewable electricity for powering the LEDs is going to essentially make the production cost considerably lower. As we said, we're now developing a 1,000 meter squared commercial facility, and the aim of this facility is to sell the produce. So we will be selling the produce, and the facility will be sustainable economically. For us as a business, our interest is to build vertical farms around the world, and if the client wants, operate them for them too. So we're really using this commercial farm we're developing both as a sort of showing that the technology works, but also showing that the business works and that it's commercially sustainable. Insofar as the TRL level, it's hard to say, insofar that we have been growing the produce, as you have seen, for now the last 6 months regularly, and supplying it both to the local restaurant and to the chef school. So now we are going to build the larger facility. So I would say we're in the TRL level 7, 8. Instead, the AI work and the deep learning work, it's at a lower TRL level. So there we have the cameras, we're getting good results, but it's still at the R&D level, and I would say it's around TRL level 4 or 5.
Okay. Thank you. Thank you very much, Benjamin. Just I was wondering concerning the collaboration, not just in Italy, but towards the other countries with vertical farming. Let's mention a commercial farm in producing basilica in Berlin. Is there any current collaboration between vertical farms? Have you been involved in any of these collaborations?
Yes, so I mean, we are aware of various vertical farms around the world. We are definitely not the only one. Germany, there is a couple. We've been working more with the UK, primarily just because I have a UK also background, and we've been working with some vertical farms in London and in the middle of the UK. This is a growing solution, and there are various players, and we think that there needs to be many players out there. The more vertical farming as a technology is accepted, the more it's potentially successful for everyone in the business. We don't think that this is one of those solutions that there needs to be only one player in the market. I think this needs to be there needs to be many players in the market to make it a mainstream technology for agriculture.
Okay. Thank you. Thank you very much, Benjamin, and thank you very much all the presentations and all the participants for the very lively chat and questions. Of course, I've saved the most important thing for the last, is that, as I was saying, it will be possible to apply for the demonstration vouchers within the next 10 days. We're very, very keen on spending the money, and we want to spend it. But we also have to acknowledge that this is an EU project, so there are certain requirements. So I would strongly suggest you to go to the vidaproject.eu and look into the document that is currently available. It is 24 pages. It takes some time to read. But just to make sure that you are in the right scope, I can hear from all the presentations today that you have very clear ideas of who you would like and how you would like to collaborate, and I think this is very important. We will do a lot to acknowledge all the different collaborations, especially the international ones. So international partners are very welcome in these projects. One thing that might be relevant to mention is that for the demonstration projects, when you read the document of 24 pages, there is the requirement that you have to use a platform called Cloud5, which is the platform that you have to use to submit the application. And we are so lucky that already next week there is a presentation of the platform. Clara, please correct me if I'm not correct, but it should be the 26th of February, again from 10 to 11.
Correct.
Thank you. So I encourage everybody to also participate there, and then open up for these international collaborations so we can get projects that makes a real impact. Thank you. Thank you again, and have a nice day, everyone. Goodbye.
Goodbye, and thank you, Morten, for this outstanding presentation and moderation. And we welcome you next Tuesday in the Clue 5 presentation in order to facilitate the proposal submission. Goodbye.
Yeah, just a good question I've seen. It will be uploaded on the web page, and when you signed into this webinar, if you tick the box where it says that you will receive the news from the VIDA project, then you will receive the information when it's ready on the web page. It should be ready shortly. It might take some time, so let's say in a week or so. If you cannot find what you're looking for on the vidaproject.eu, then go to the page says partners, and then you have all the local partners. You can contact them directly, and they will answer you as soon as possible. Thank you again, and